Elasticity. Next chapter, elasticity. What is elasticity? Okay, elasticity. During the study of mechanics in either chapters, we had started with the concept of massive, small particles and then the rigid body, which we defined as one in which the distance between any two particles remains unaltered. Okay. What we got, the external forces applied to it. In other words, the body remains undeformed. Okay, the body remains undeformed in its shape, size, and volume. Okay, how you got? In practice, we never find such a body. Every material body gets deformed to a smaller or larger extent depending upon the way in which the forces act. Moreover, it has a tendency to recover its original shape and size, and removal of external applied forces within some limit called as elastic limit. Okay. Okay, this property of a body is known as elasticity. Okay, elasticity is the property by virtue of which material body regain their original shape. The property elasticity is the property elasticity is the property Elasticity is the property by virtue of which material bodies regain their original shape, and size, after the external deforming force are removed. External deforming forces are removed. Okay. Elasticity is a property by virtue of which material bodies regain their original shape and size after the external deforming forces are removed. Okay. If you can stress this material, then you let this is rubber, and you stress this material, and this is another shape is required, another shape is achieved, and after removal external force, this regain its original position at this line. Okay. So you can show that elasticity is the property by virtue of which material bodies regain their original shape and size after the external deforming forces are removed. Okay. Then when an external force acts on a body, there is a change in its length, shape, and volume. The body is said to be strand. Such bodies are called elastic bodies. Some of the examples are steels. Examples: steel. Steel is a elastic body. Glass is elastic body. Ivory is elastic body. Quartz, rubber, etc. Okay. The The body who do not regain their original shape and size are called plastic bodies. Okay, the bodies who do not regain their original shape and size are called plastic bodies. Okay, the bodies who do not regain their original shape and size are called plastic bodies. Are called plastic bodies. Okay, body. And steel glass are more elastic than rubber, liquid, and gases are highly elastic. Okay, steel glass are more elastic. Steel glass are more elastic. Steel glass are more elastic than rubber. Okay. Steel and glass are more elastic than rubber. Liquids and gases. Gases are highly elastic. Okay. Liquid and gases are highly elastic. Okay, liquid and gases are highly elastic. Okay, in this chapter our discussion will be confined to those bodies which are homogeneous, means having a uniform composition and isotropic, whose properties are the same in all directions. Metals in the form of wires or rods behave as isotropic bodies for elastic properties. Solid mostly crystals show different properties in different directions and are thus called non-isotropic or anisotropic. Okay, anisotropic. Okay, stress and strain. Stress and strain. Stress and strain. Okay, stress and strain. Okay, what is stress and what is strain? Okay, when an external force acts upon a body, relative displacement of its various parts takes place. The displaced particles tend to come to their original position to restore the original length, volume or shape of the body and thus exert a restoring force. The restoring force per unit area which comes into play inside the body is called the stress. Okay, the restoring force per unit area. Okay, unit area which comes into play inside the body. Which comes into play inside the body is called the stress. Okay, when an external force acts upon a body, relative displacement of its various parts takes place. The displaced particles tend to come to their original position to restore the original length, volume or shape of the body and thus exert a restoring force. The restoring force per unit area which comes into play inside the body is called the stress. The reaction set up in the body is equal and opposite to the applied force. Okay, equal and applied force which comes into play inside the body is called stress. The reaction setup in body is equal and opposite to the applied force. So long as there is no permanent change produced in the body, the restoring force is therefore equal to the applied force. Hence, if the force F is applied normally, if the force is applied normally to the area of cross section of a wire, then hence if the force F is applied normally to the area, normally applied to the area of cross section of a wire, then stress equal to force upon area, okay. The external force acting on a body causes a relative displacement of its constituent particles. A change in the length, volume and shape take place. The body is then said to be under a strain, okay. A change in the length, volume or shape take place. The body is then said to be under a strain, okay. Strain. What is strain? We will be study about strain, okay. Strain. What is strain? You can listen carefully. Strain is defined as the ratio of the change in length, volume or shape to the original length, volume or shape. Strain is thus a pure ratio and has no units, okay. Strain is defined as the ratio of the change in length, the ratio of the change in length, volume, or shape to the original length, volume or shape to the original length, volume or shape, volume or shape. Strain is thus a pure ratio. Strain is thus a pure ratio and has no units okay. Strain, okay. The ratio of the change in length, volume or shape to the original length, okay, volume or shape. Strain is thus a pure ratio and has no units, okay. Next heading is small deformation and Hooke's law, okay. We will be study about the small definition and Hooke's law. What is small definition? What is Hooke's law? Okay, good. Small deformation and Hooke's law. Okay. In 1676, Robert Hooke discovered a linear relationship between stress and strain for small deformation with elastic limit. This relation is known as Hooke's law. Okay. in 1676. In 1676, Robert Hooke discovered a linear relationship between stress and strain for a small deformation within elastic limit. This relation is known as Hooke's law. Okay, for stress within the elastic limit of a material, the strain produced is directly proportional to stress applied. Okay, according to Hooke's law. Okay, according to Hooke's law. According to Hooke's law, for stress, for stresses, within the elastic limit, within the elastic limit, for stresses within the elastic limit of a material, the strain produced is directly proportional to the stress applied. Okay, okay. For stress within the elastic limit of a material, the strain produced is directly proportional to the stress applied. Thus, within the elastic limit of a material, stress is directly proportional to strain. Okay. Then stress upon strain equal to constant. Okay. The constant is called the modulus of elasticity of the material. Okay. The constant is called modulus of elasticity, of the material, okay. The SI unit of modulus of elasticity and is Newton per square meter. Okay, and SI unit of constant is SI unit of constant, that means modulus of elasticity is Newton meter square r Newton per meter square r Newton meter minus 2 square. Okay, and its dimension are those of stress is that, and dimension is m to the power 0, l to the power minus 1, t to the power minus 2. Okay. Next heading, elastic constants for an isotropic solids. Elastic constant for an isotropic solid. Okay. Elastic constants elastic constants for an isotropic solids. Okay, solid. Okay, elastic constant for an isotropic 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 solid. Okay, according to the nature of strain, there are three moduli of elasticity of an isotropic material. There are first is Young modulus. First is Young modulus. Young modulus. Young's modulus. Second is bulk modulus. Second is bulk modulus. Bulk modulus. And third is modulus of rigidity. Modulus of rigidity. Okay, modulus of rigidity. Okay, then the first Young modulus is denoted by capital Y, and bulk modulus is denoted by capital K, and modulus of rigidity is denoted by eta. Okay, then first Young's modulus. First is Young's modulus. Okay, Young modulus. First is Young modulus. Okay, then it is defined as the ratio of stress to longitudinal strain within an elastic limit. It is defined as the ratio of stress to longitudinal strain longitudinal stress. Okay, longitudinal stress. Okay, it is defined as the ratio of stress to longitudinal strain within elastic limit. Within elastic limit. Okay, limits. When a change of length takes place, the strain is known as longitudinal strain. Okay, when a change of length when a change of length take place, the strain is known as longitudinal stress. Is known as longitudinal strain. Okay, longitudinal strain. Okay, it is measured by the change in length per unit length. If L is the length of the wire and an increase in small l in the length is caused by a force, then strain equal to L by capital L, where small l increases length and capital L is the original length. Capital L is the original length. Okay, and hence young modulus of elasticity, hence young modulus, young modulus of elasticity, young modulus of elasticity, that is denoted by y, that is denoted by y equal to stress, upon strain, that is f by a and divided strain is small l by capital L, that is FL by AL, and the unit this is the equation number first. Okay, this is the equation number first. Okay, this is equation number first. And so young modulus of elasticity y equal to stress upon strain, then that is F by A by L by capital L equal to FL by AL. Okay, FL by AL. Okay, then and second bulk modulus, second is bulk modulus, second is bulk modulus, okay, 1 minute. Bulk modulus, okay, it is defined as the ratio of stress to volumetric strain. It is the ratio of stress, to volumetric strain, okay. It is the ratio of stress to volumetric strain when a force is applied normally to the surface of a body and change in volume takes place. The strain is known as volumetric strain. Okay, when a force is applied, normally to the surface, normally to the surface of a body, and change in volume and change in volume takes place, okay. When a force is applied normally to the surface of a body and change in volume takes place, the strain is known as volumetric strain. The strain is known as volumetric strain, okay. Volumetric strain. It is measured by change in volume per unit volume and is equal to small v by capital V, and this is also small v by capital V, where small v is the change in volume produced by the force F in the original volume V, where small v is a change in volume, change in volume produced by the force capital F in the original volume capital V. Hence bulk modulus K is given by F by A. Bulk modulus. Modulus means F by A, that is small v by capital V. F by A divided by small v upon capital V, that is capital F capital V by AV, that is PV by small v, that is P by V by capital V. This is the equation number 2, where F by A equal to pressure, applied pressure, okay. When a very small pressure dP is applied, the change in volume being very small is represented by dV, then K equal to minus dP upon dV by V. Okay. The negative sign indicates that an increase in applied pressure causes a decrease in volume. Minus sign indicates that an increase in applied pressure causes decrease in volume. Okay. And next, third point, modulus of rigidity. Modulus of rigidity. Modulus of rigidity. Okay. Third point, modulus of rigidity. Okay. The coefficient or modulus of rigidity is defined as the ratio of the tangential stress to shearing strain. This is the ratio. This is the ratio of the tangential stress. Tangential is the ratio of tangential stress to shearing, tangential stress to shearing strain. Okay. To find the value of the shearing strain, consider a solid cube ABCD. Consider a solid cube ABCD. 1 minute. This is the consider a solid cube ABCD. To find the value of the shearing strain, consider a solid cube ABCDEFGH. ABCDEFGH. Okay, EFGH. Consider a solid ABCDEFGH. Okay. The lower face CDGH. The lower face CDGH is fixed, and tangential force F is applied. Okay. Over the face ABEF. Okay. ABEF show that it is displaced to the position of A dash, B dash, E dash, F dash. Each horizontal layer of the cube is then displaced, the displacement being proportional to its distance from the fixed plane. Then shearing strain, then shearing, shearing strain, shearing strain is displacement of plane, is a displacement, is a displacement, the displacement of a plane, displacement of a plane upon distance from the fixed plane, distance, distance from the fixed plane, from the fixed plane, distance from the fixed plane, okay, fixed plane. Then A dash upon AD equal to small l by capital L, that is tan theta, that is tan theta. A dash upon AD, A dash upon AD, A dash upon AD equal to L by capital L, that is tan theta, okay, where theta is small, when theta is small, theta is small, then tan theta is theta, then shearing strain, shearing strain equal to theta. Hence the angle through which a line original, hence the angle, which a line originally, when a line originally perpendicular to the fixed plane, 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 it is turned, plane is turned, is a measure of the shearing strain, is a measure of the shearing strain, okay. Hence the angle through which a line originally perpendicular to the fixed plane is a measure of the shearing strain, okay. Now modulus of rigidity, now modulus of rigidity, now modulus of rigidity, now modulus of rigidity equal to tangential stress, tangential stress upon shearing strain, okay. That is eta equal to F by A whole upon theta, that is F upon theta A, that is T by theta. This is the equation number 4, where A is the area of the face, where A is the area of the face, area of the face, ABEF, area of the face, ABEF, okay, ABEF, and T is the tangential force applied per unit area, and T is the tangential force applied, T is the tangential force applied, and T is the tangential force applied per unit area, applied per unit area, applied per unit area. Okay, and next point is Poisson ratio. Next point, Poisson ratio. Okay, what is Poisson ratio? We will be study about Poisson ratio. Okay, Poisson ratio. Poisson ratio. Okay, Poisson ratio. When a wire is stretched, its length increases, but its diameter decreases in general. Okay, when a wire you take this is a wire. Okay, you let this is a wire. When we stretch, we will be stretched, then its length is increases, but its cross-sectional area decreases. That means its diameter is decreases in general. Okay, when an elongation is produced by a longitudinal stress in a certain direction, contraction results in the lateral dimensions of the body under the strain. The lateral strain is proportional to the longitudinal strain so long as it is small. Okay, the ratio lateral strain, the ratio lateral strain, the ratio lateral strain upon longitudinal strain, longitudinal strain is called Poisson ratio. Poisson's ratio. Okay, Poisson's ratio, and is denoted by the letter delta. Delta. Okay, and it is denoted by delta. That is length. Let the length of the wire capital L, diameter of the wire capital D increase in length small n and corresponding decrease in diameter small d. The Poisson ratio equal to small d upon capital D and small l by capital L, that is beta by alpha, where the small d is the decreases diameter of the wire, capital D is increases diameter of the wire, and small l small d is the decreases of diameter, and capital D is the original diameter, and small l is the small. The Poisson's ratio is beta by alpha. Okay, this is the equation number 5, where beta is the lateral strain, where beta is the lateral strain. Okay, lateral strain, and alpha is the longitudinal strain. Okay, longitudinal strain. Okay, beta is the lateral strain and alpha is the longitudinal strain. Poisson's ratio is dimensionless quantity. Dimensionless quantity. Okay, dimensionless quantity. Okay, third point, 4 point, and that means next heading, glass is more elastic than rubber. Glass is more glass is more elastic glass is more elastic than rubber. Okay, this is because for a given stress, the strain produced in glass is much less than that in rubber. Okay, suppose for a rubber, young modulus, suppose for rubber, suppose for rubber, young modulus y1 is suppose Young's modulus y1 is y1 equal to capital F capital L by A L1. Okay, and for glass y2 equal to capital F capital L by A L2. Okay, for the two materials F and L, F, L and A remaining the same, then L1 for the rubber is more than L2 for the glass. Therefore, Y1 is greater than Y1. Okay. Then Y1 for the two materials F, L and A remaining the same. Remaining the same. L1 for rubber is more than L1 for rubber is more than L2 for glass. L2 for glass. Then therefore Y2 is greater than Y1. Okay. Limit yield point elastic fatigue next heading. Okay. Limit yield points elastic fatigue. Limit yield point and elastic fatigue. Limit yield point and elastic fatigue. Okay. Limit yield point elastic fatigue. Limit yield point elastic fatigue. Okay. Elastic limit. Okay. Elastic limit is the maximum stress. Elastic limit is the maximum stress within which the body exhibits the property of elasticity. Okay. Elastic limit is the maximum stress. Elastic limit is the maximum. Elastic limit is the maximum stress. Within which the body exhibits. The property of elasticity. Exhibits the property of elasticity. Okay. Elastic limit is the maximum stress within which the body exhibits the property of elasticity. Below the elastic limit, the body regains its original position. Below the elastic limit, below the elastic limit, below the elastic limit, the body regains its original position. Limits, the body regains its original position, original position, our shape, our size, our shape, our shape, our size, our shape, our size, when the deforming force, when the deforming force, when the deforming force is removed, okay? Removed. Beyond the elastic limit, the body does not regain completely its original position or shape or size. Beyond the elastic limit, beyond the elastic limit, the body does not regain completely its original position, its original position, our shape, our size, our size, even though the external force is withdrawn, even though the external force, is withdrawn, okay? Second point, yield point. Second is yield point, okay? Second, yield point. When a wire is loaded beyond the elastic limit, Hooke's law is no longer obeyed, and the extension produced in the wire is not proportional to the stress. Okay? You can show in the figure, and shows stress strain curve for a wire. The extension is more than the corresponding increase in stress at this stage. The particles of the material go further apart. Now, if the load is withdrawn, the particles do not regain their original position, point B. Original position, point B, okay? And you can represent it yield point. B is represented yield point, okay? Okay? Yield point, okay? Yield point, okay? You can show yield point, point A, point B, point C, point D, okay? Stress, strain, okay? Yield point. When a wire is loaded beyond the elastic limit, when a wire loaded beyond when a wire loaded beyond the elastic limit, beyond the elastic limit, Hooke's law is no longer obeyed. Hooke's law is no longer beyond no longer beyond, no longer beyond, sorry, Hooke's law is no longer obeyed, and the extension, and the extension, and the extension produced in the wire, produced in the wire is not proportional to, is not proportional, is not proportional to, not proportional to the stress, to the stress, to the stress, okay? When a wire loaded beyond the elastic limit, Hooke's law is stress no longer obeys, and the extension produced in the wire is not proportional to the stress, okay? Here you can show the stress strain curve of a wire. This is the stress strain curve of a wire. The extension is more than the corresponding increases in stress. At this stage, the particles of the material go further apart. Now, if the load is withdrawn, the particles do not regain their original position point B. Okay? The extension is more than the corresponding increase in stress. The extension is more than, the extension is more than, the extension is more than the corresponding increase, more than the corresponding increase in stress, at this stage, the particles of the material go further apart. The particles of the material, go further apart, okay? Go further apart. Now if the load is withdrawn, now if the load is withdrawn, the particles do not regain their original position. Particles do not regain their original position. Okay? And if the load is withdrawn, the particles do not regain their original position, point B. Okay? Represents yield point. Point B represents yield point. Point B represents yield point. Okay? Yield point. When a wire loaded beyond the elastic limit, the Hooke's law is stress no longer obeyed, and the extension produced in the wire is not proportional to the stress. The extension is more than the corresponding increases in stress. At this stage, the particles of the material go further apart. Now if the load is withdrawn, the particles do not regain their original position. Point B represents a yield point. Okay? Elastic fatigue. Next point, elastic fatigue. First is elastic limit, second elastic yield point, and third is elastic limit. Okay? Elastic limit. Okay? If a body is continuously subjected to strain stress and strain. If a body is continuously subjected, if a body is continuously subjected to stress, subjected to stress and strain, after some period, it gets fatigue. Okay. Consider two torsional pendulum A and B having similar wires. A is set into vibration after A has come to rest. Both the pendulum A and B are set into vibration simultaneously. It is found that due to elastic fatigue, A comes to rest earlier than point B. A comes to rest earlier than point B. Okay. Consider if a body is continuously subjected to stress and strain, after some period it gets fatigue. Consider two torsional pendulum A and B having similar wires. A is set into vibration after A has come to rest. Both the pendulum A and B are set into vibration simultaneously. It is found that due to elastic fatigue, A comes to rest earlier than B. Okay. Next one, work done in stitching a wire. Next heading, work done in stitching a wire. Okay. Next heading, work done in stitching wire. Okay. Work done in stitching wire. Okay. Work done in stitching wire. Okay. Whenever a body is deformed by application of external forces, the body gets strained. Okay. The work done is stored in the body in the form of energy known as energy of strain. Let us calculate the work done in stitching a wire producing longitudinal strain. Consider a wire of length L. Area of cross section A. And Young modulus of elasticity Y. Let small l be the increase in length. When a stretching force F is applied. Okay. Small l be the increase in length when a stretching force F is applied. Okay. The Young modulus of elasticity. Young modulus of elasticity. Young modulus of elasticity Y equal to F capital L by A small l R. F equal to YAL by capital L. And work done in producing or stitching. Work done in producing or stitching producing a stitching DL equal to FDL equal to YAL upon capital L multiply DL. Okay? Hence work done to produce, hence work done to produce, or stitching of the wire from 0 to L. Okay, then work done W equal to 0 to L YAL by capital L DL, that is YA upon capital L square by 2 0 to L. Then this work is 1 by 2 YAL square by capital L, that is 1 by 2 YAL by capital L multiply L. Okay, that is 1 by 2 F multiply L, and that is 1 by 2 multiply stretching force 1 by 2, this is F is stretching force multiply stretching force multiply elongation produced, multiply elongation produced. Okay, elongation produced. Okay, this is the work done in stitching a wire. Next, studying the relation between Young modulus and relation. Okay, we will be relation between Young modulus, bulk modulus, and next sigma. Okay, thanks.